Okay, in this lesson we're going to summarize the remainder theorem. So remember when we talked about the remainder theorem, we talked about how whenever you are writing a division statement that involves numbers or even expressions, you can rewrite the division statement using multiplication and addition instead. So here's an example here. If you have 2,282 divided by 7, that gives you a result of 326. So if I take this number and I divide it equally into groups of 7, I get 326 as my result. Okay. Now I can rewrite this as a statement that involves multiplication instead. And the way I can do that is by taking the divisor that I have here, which is 7, and multiplying that divisor on both sides to get a result of 2,282 is equal to 7 times 326. Okay. So here we're going from quotient form into a different form where we can actually check our answer. Or you might get an example such as 700 divided by 15. Now the special thing about this example is that 700 does not go into 15 evenly, and so what you end up with is a remainder. Okay, so what this means is if I take this number, 700, and I divide it by 15, I get 46 whole, plus I get a remainder of 10 over the divisor, which is 15. Okay, and again, to check your work, you can rewrite this in multiplication and addition form. And the way you do that is by multiplying both sides by the divisor, which is 15. And once you do that, what happens is on the left-hand side, you're left with 700. And on the right-hand side, you're multiplying each term by 15. So you get 15 times 46. And then the last term here, which was a fraction, once you multiply by 15, the 15 reduces with the 15 in the denominator to leave you with 10. Okay, so here you have the dividend, which is a number you are dividing. You have the divisor, which is the number that you're trying to divide the dividend by. Then you have the quotient, which is the number of times it goes in evenly. Plus you have the remainder, which is the amount that doesn't go in evenly. Okay, so if you actually did long division with that last example, here's your divisor going into the dividend. And there's the quotient. That's the number of times it goes in evenly. Plus there's a remainder at the very end, which is a remainder of 10. Okay, and again, this is if you look at it in quotient form, we saw it above, 700 over 15 gives you 46 whole, plus a remainder of 10 over the divisor, which is 15. And if you wanted to write this in a form where you can check, you can multiply it by the divisor, and so you'll get something like 700, which is the dividend, 15, which is the divisor, 46, which is the quotient, plus the remainder, which is 10 in this case. Okay, we're going to apply this to polynomials in a few minutes. So we can apply the same idea with polynomial division. So remember that long division can also be used to divide a polynomial by a binomial. So if you have a polynomial like the one that I have here, divided by a binomial like x plus 1, you can also look at this thing by writing it as in long division form, the kind of the method you would use to do long division. So x plus 1 dividing into 2x cubed plus 4x squared minus 2x plus 1. And so what would happen is that the result of the division of a polynomial function, p of x, by a binomial of the form x minus b, much like the one we saw, can be written in the form p of x divided by x minus b equal to q of x plus r over x minus b. So what this means is if you take the polynomial and you divide it by the binomial, you'll end up with a quotient plus some remainder over the binomial that you started with. So it's the same idea. If you actually think about the different terminology we looked when you were looking at numbers, when you're dividing a polynomial by a binomial, you have p of x over x minus b, q of x plus r over x minus b. The corresponding statement that can be used to check the division is p of x equals x minus b times q of x plus r. So all this means is, in order to check your division, you would actually multiply the left side and the right side by the divisor. And in this case, the divisor is x minus b. What ends up happening on the left-hand side is that you're left with the original polynomial, which is your dividend. Then you're left with your quotient multiplied by the binomial, which is your divisor and your quotient here. Plus, if you multiply this by your divisor, which is x minus b, you're left the remainder. Okay? So if this is the division statement or the quotient statement that you started with, this statement here, p of x equals x minus b times q of x plus r, is actually a statement that you would use to check your work. Okay, so that's something to remember. Okay, for the first example, it asks us to divide 4x cubed plus 9x minus 12 by 2x plus 1. And then it asks us to identify any restrictions on the variable. And then finally, we're going to write the corresponding statement that can be used to check the division. Okay, so I'm going to do this on a separate sheet of paper so I have more room. And so what I'm trying to calculate is 4x cubed plus 9x minus 12 divided by 2x plus 1. Okay, so now I can hide the other page. And so what I'm going to do is I'm going to write this using long division so I can actually divide it out. And so I have 2x plus 1 being divided into 4x cubed plus 9x minus 12. Now the problem here is that you'll notice that the quadratic term is missing. So whenever you're doing long division, remember to include the quadratic term or any of the missing terms that might be there. So I'm going to add 0x squared plus 9x minus 12. And the reason for this is because eventually when you try to start figuring out your quotient and you start doing the long division, you will end up with a quadratic term, so you want to make sure that's there to help you when you're subtracting. Okay, so going back to long division here, remember whenever you are doing long division, your goal is to try to figure out what needs to be multiplied by the first term here to get the first term of the dividend. So here's my divisor, here's my dividend, and I'm going to try to start finding out my quotient. So if I'm trying to figure out what needs to multiply by 2x to get 4x cubed, that answer is 2x squared. So I'm going to do long division here. And so I'm going to multiply what's part of my quotient so far, 2x squared, with what's part of my divisor right now, which is 2x. And so far that gives me 4x cubed. And I'm going to do 2x squared plus 2x squared times 1, and I'm going to get positive 2x squared. And so this is the reason why it was important to include that quotient term, even though it's 0x squared, and because I'm going to be subtracting them eventually. Now if I subtract these two expressions, so far I get 0 for my cubic term, and 0 minus 2x squared will give me negative 2x squared for the quadratic term. I'm going to bring down the 9x. And I'm going to do the same thing again. Something times 2x has to give me negative 2x squared, and that's negative x. And so if I multiply the divisor with negative x, I get negative 2x squared minus x. And again, if I subtract the two, the first terms will cancel out. Second terms give me 10x. I'm going to bring down my constant term. And again, same thing. 2x multiplied by something has to give me 10x, and that's by 5. And so that gives me 10x plus 5, and if I subtract again, I get negative 17. So if I'm writing this using division, I have 4x cubed plus 9x minus 12 divided by 2x plus 1 gives me a quotient of 2x squared minus x plus 5 plus a remainder of negative 17 over the divisor, which is 2x plus 1. Okay, so here's my quotient part, 2x squared minus x plus 5, and there's a remainder over the divisor. Okay, the second question asks us to state any restrictions, and in this case there are going to be some restrictions because you have a variable in the denominator whenever we're dividing. So in this case, if you have a variable in the denominator, there will be a restriction on the variable, and the value of x that can make the denominator 0 creates a restriction. So in this case, our restriction is that x cannot equal negative a half. Okay, so there's a restriction. And then finally, the last part of the question asks us to write the corresponding statement that can be used to check our work. And so what that means is we're going to take our division statement and we're going to multiply the left side and the right side of our division statement, or our quotient form. We're going to multiply both sides of it by the divisor so that we can actually check our work. So what I'm going to do is multiply the left side by 2x plus 1 and multiply the right side by 2x plus 1 as well. So what I end up with on the left hand side is 4x cubed plus 9x minus 12, which is my original polynomial. On the right hand side I have the divisor, which is 2x plus 1, multiplying with the quotient, which is 2x squared minus x plus 5. And then finally, when I multiply the last term here by 2x plus 1, all I'm left with is a remainder, which is minus 17. So what this means is I should be able to expand and simplify that expression, and that should give me the polynomial that I started with. And I'm going to do that just to show you what would happen. So if I expand the binomial with the trinomial, so far I get 4x cubed minus 2x squared plus 10x plus 2x squared minus x plus 5, and then I have minus 17 at the end. And if I simplify this, I get 4x cubed. These guys cancel out. Plus 9x minus 12. So there you go. Okay? So it shows you that I get the exact same thing whether I look at it in multiplication form or in quotient form that's here. Okay, so the second last slide here looks at what the actual remainder theorem is. So the remainder theorem is actually a quick way to figure out the remainder when a polynomial is divided by a binomial. Okay, so it says when a polynomial function p of x is divided by x minus b, the remainder is p of b. When a polynomial function p of x is divided by ax minus b, the remainder is p of b over a, where a and b are integers and a cannot equal 0. Both of these sort of mean the exact same thing. All it means is that if you solve for x in each of these binomials, and so this would be x equals b over a, and you plug it into the polynomial, the remainder that you get is the exact same remainder you would get when you actually do long division. Okay, so this is just a quick way to figure out what the remainder would be. Okay, and so for example, if I show you what we did in the previous example, we were dividing 4x cubed plus 9x minus 12 by 2x plus 1. And so what this means is if I try to figure out the remainder using the remainder theorem, I should end up getting negative 17 again. Okay, so let's say p of x is the polynomial we were dividing. And yes, I realize my paper is upside down, but I'm just trying to show you guys something. And if I plug in the value of x, it would make the denominator 0, which in this case is negative 1/2. And I solve this, I should get the exact same remainder that I had earlier. So if I look for p of negative 1/2, I get 4 times negative 1/2 cubed plus 9 times negative 1/2 minus 12. And if I simplify this, I get 4 times negative 1 over 8 minus 9 over 2 minus 12. 4 times negative 1 over 8 is negative 1/2. Negative 1/2 minus 9 over 2 minus 12 gives me negative 10 over 2, which is negative 5, minus 12, which is negative 17. That's the exact same remainder that I had earlier as well. Okay, example 2 says when p of x is equal to 2x cubed minus kx squared plus 3x minus 2 is divided by x plus 1, the remainder is negative 12. Determine the value of k. So in this case, because it tells me the remainder is going to be negative 12, it makes me think about the remainder theorem. And so what it's telling me so far is that when I divide p of x by x plus 1, I get a remainder of negative 12. So thinking back to the remainder theorem, what this means is that if I look at p of x equal to negative 1, then my result should be negative 12. The remainder should be negative 12. Okay, so what I'm going to do is I'm going to look for, or I'm going to solve for p of negative 1 using the polynomial that's given. And then I'm going to replace p of negative 1 with negative 12, and then using that I should be able to solve for k. So p of negative 1 is going to equal 2 times negative 1 cubed minus k times negative 1 squared plus 3 times negative 1 minus 2. And I know that p of negative 1 is negative 12, so I can substitute that in. And the rest of it on the right hand side I should be able to just evaluate. So I get 2 times negative 1 minus k times 1 minus 3 minus 2. Then I'm going to continue to evaluate the right hand side. I get negative 2 minus k minus 5, which is negative 12 equal to negative 7 minus k. And now from here I can just solve for k. I'll add 7 to both sides to get negative 5 equals negative k, which means k is equal to 5. Okay, and if I plug in k equal to 5 into the original polynomial, so if I replace this with 5, then I should be able to check my work by actually doing long division to see that the remainder is negative 12. Okay, so the answer was k equal to 5.